Welcome back to our final video of today's DECA 2 lecture. So far we have seen how Swan Assist can be used to automate or semi-automate the way to infer security relevant methods from arbitrary code bases. And in this final part, which will be shorter, we are going to see how these methods can be used in combination with domain-specific languages to specify rules for detecting tame flaws. And most of the applications are in detecting security vulnerabilities. We are going to see two examples of domain-specific languages. So we said that many of these SaaS tools are providing such kind of languages. The idea is that the users can configure the tools to work better because often they produce high number of false positives, or sometimes there are some new vulnerabilities or new or specific tame flaws that the existing rules cannot detect, so users can specify this for their code bases. And these DSLs are very often focused on the experts, I would say, because they require a quite deep understanding of static analysis and also in security. And we are going to see the first DSL example like this, which is more focused on security experts. And as a second example, we are going to see a new DSL which was recently designed in our research group, and it is I would say more simple and more tailored to software developers. So the first DSL is the one from SAML, and it's called CodeQL. SAML was bought recently by GitHub, and if you're using GitHub, you very likely have your code very likely have been analyzed by this engine. So they have a data flow engine, and this engine has also a tame tracking module. So there are specifications for tame tracking, like this one here. We have one example for SQL injection, and we will walk through now this code to see how this language works and how users can specify the rules here. So the language is itself declarative language, and it includes also object-oriented concepts because one can specify classes, and also it is kind of SQL-like because the main query is actually in lines 23 to 25. We have from, where, and select clauses. This language, you see, you can import very different modules. They have implemented many different supports for different frameworks. They also support not only Java but other languages, and there is a specific taint tracking module. And so what this taint tracking module actually provides a taint tracking class which is of type configuration. This is in line 33. Before we go to this, we will see now how the query looks like. So we have a from part where you can define kind of objects, and these are like they can be of different type of class, and you see we are using different predefined classes. We have class that models a path node, and we will need two of them, one for source, one for sink, so we can have two objects of this type. And then we can have a specific type of sink, which is modeled by this query injection sink class. This is predefined class, and in this case this is already implemented, and this class is actually kind of implementing a pattern matching of typical sinks for injection. So this is exactly where our lists of sources and sinks will come from, and CodeQL can do this in a pattern matching way, I would say. You see, this language also supports predicates, so users can define their own predicates, like query tainted by, it's the predicate defined here in line 27 to 30. And so that is, as I said, declarative language, so everything where that returns true in this where clause, if it is evaluated true, then this query will return the result specified in the select parse. So the result of this query will return the query itself, the source location, the sink location, and it will return a message. So you can construct messages like this. Query might include code from source this user input. Okay, so we can see here the predicate. The predicate is something like method, like function, and it takes as argument three objects. We have a query injection thing, and then we have two path nodes, and it uses this exist operator where we say if there exists, return a configuration, so of type query injection flow config, where exists a path, has a flow path from source to sink, and the sink is of type query, and the query is a predefined class. So we're not going to have a look into these implementations. If you're interested, you can open this in Eclipse, for example, and go through them, and they are all available. You can modify those classes or write your own classes. It's a very expressive language. You can have a quite good you have quite good expressivity of the whole graph structure of the code. And because we are doing a taint analysis, you see we have a taint tracking class which we have implemented. Actually, we can create a class that extends this taint tracking configuration, and this has a 3 predefined predicates, so we need to override them. We have a predicate is source, is sink, and is sanitizer, and in each of these predicates you can implement the way you want to match the sources and the sinks. So you could here even have like a matching signature of specific methods, but in this example there are specific classes called remote flow source that model sources, and query injection sink that models sinks. So this is the first example what we wanted to show you, and the second one is another domain specific languages which you can achieve the same taint tracking specification, but this is actually in Java internal DSL. This means the entire DSL is within the Java language. So we have used the builder pattern to build this. So the way it works, it's a complete Java code. We have defined some classes that you can use, and we have a static part, which is this upper part, like where we have specific definitions of methods, and these are actually the sources, sinks, the sanitizers, and like the other, and validators. You can define them, and the idea is you can read them as in Fluent style. So you can have this kind of methods in other classes and modules, so you can use the entire Java infrastructure to enable reusability of them, so you can specify such methods once for a specific library and then reuse them. And how we are doing that is by giving the method signatures here into the definition of a method, and with this out in parameters and so on, we are specifying what exactly we want to taint for by this method call. So we have an example here of source1, which is a get parameter. We are saying that the out, so the information flowing out of this method is actually relevant for us, and that is the return type. So the return value of get parameter is what we are going to taint in our analysis. So that will be the taint. Similarly, if you want to specify like sinks, you can have like in, that means flowing into the method. So in this print writer append method, the first parameter would be the relevant part that your analysis needs to know about, and then we can say that in parameter from 0, that means the first parameter of this method. So there is support of different kind of things here, but it's relatively simple to learn to express this kind of SRMs. And then that, as I said, that is done once. Once you have specified your SRMs, you can create queries for your applications and for your analysis. And queries are always specified again in creating objects from type taint flow query. In this case, we have an example for cross-site scripting vulnerability. You can see here you call the constructor, then you can call this chain of methods like from, where you will say from where. So we want to track from source 1, not through sanitizer, so not going through the sanitizer, to sync for XSS, so reaching to sync access, then report. You can give a message name that should be reported to the user, so we can say reflective access as vulnerability, at location, and then you can specify some location. For example, we chose here to give the location of the source. The idea is that you can read this language quite like a sentence, so it can be like from source 1, not going through sanitizer, reaching to sync, we want to report a message. And then yeah, you can also use like here in NoSQL i2 have an AND operator where you can combine multiple taint flows in parallel. And yeah, this is very tailored to taint analysis, so compared to CodeQL, this is much less expressive, but we have done a usability study recently showing that software developers find this language much more usable and understandable. And yeah, if you're interested in this, you can have a look at our project that involves the development of this language. It is already also open source, and we have quite some examples that you can have a look and try it on your own. It is also implemented for multiple IDEs, so you can use it in Eclipse, in IntelliJ, in Visual Studio Code, and for a few more. Yeah, so this was just two small examples of DSL, so we wanted to show you how these security relevant methods are actually in practice used in combination with domain-specific languages. And yeah, final words. I would like here to conclude what we have seen in this lecture. We have introduced Swan as a supervised machine learning approach that takes an arbitrary code base as input, and it can classify all methods from this code base into different security relevant methods. and then further classify them into security vulnerability types. Additionally, we also see how the precision of this classification can be improved by introducing a semi-automatic approach, Swan Assist, where users can manually label methods from their code base and add them to the training data. Our experiments also show that users will need relatively low number of methods to manually label when they use our Swan Suggester algorithm to label the methods. And then in the final part, we have seen now two examples of domain-specific languages that are used in combination with the inferred security-relevant methods. And this is very often done in many of the tools that exist today and are available. Yeah, with this, I will conclude here this talk. Thank you for your attention and bye-bye.